for joining. Thank you, Harika, for the introduction. So today's talk is about both quasars and how do we know what we know. Basically, we do not have the luxury of walking into our chemistry lab and like rolling our flasks. We do not have the luxury of going into our bio labs and poking needles in rats. As astronomers, we are only limited to Earth, and all of our subjects lie in deep space. And the only thing that we get from them is light. So basically, what our astronomers tell us, how do they know that? Are they just speaking stuff made out of their mind, or they have some sense in that? So we'll be talking about quasars. So what are quasars? This is a typical spiral galaxy, which is just existing. There is a supermassive black hole in the center of the galaxy, everything, and these are the dust and the stars. When it gets hungry, the central supermassive black hole, when it starts to feed, it gets converted into an active galaxy. So what does an active galaxy actually means is the central supermassive black hole is feeding on the matter. It's feeding on stars, it's feeding on gas. So that is basically what an active galaxy is, and quasar is a type of active galaxy. How did we know that there exists such an item? So unfortunately or fortunately we say, but because of the World War, some radars and dishes were invented to look at the enemy planes. But when they were pointed up at the sky, we saw such blobs in the sky that were radio loud, which means that something in the sky was emitting huge amounts of radio waves. But we didn't know what they were because the telescopes had a very poor resolution. So all these things look like blobs. So we were not able to tell what exactly are those. Until one day the moon crossed this object, 3C273. So as soon as the moon covered this object, there was a sudden drop in the radio waves from that section of the sky. We immediately knew that that radio source is coming out from a small star. So all the optical telescopes were pointed on that star. It somewhat looks like that. This is the Hubble image of 3C273, and this is a star in the background for your comparison. You will be seeing that there is not much difference in those two objects, just it's a slightly bit brighter. So that is what gave the name quasar. Quasar is a short form for quasi-stellar radio source. It looks like a star, it is a radio source, but it is not a star, hence the quasi-stellar radio source. Above here you will see a spectrum of a star, and this is the spectrum of a quasar. A significant difference, if you can note, is in this spectrum you will see massive drops. These points, these are the absorption lines. Whereas in a quasar spectra, we see peaks instead of a drop. So what does it mean? The drops are absorption spectrum. Absorption spectrum is created when light passes through gas and some of the light is captured or absorbed by the gas, so we see a massive dips. Whereas these emission lines are created when something is heated up. It heats up, the electrons jump on to higher levels, they fall down, physics, and they generate these kinds of emissions. So that was a massive difference between the two spectrums, which led to a confusion amongst the astronomers. Well, the previous spectra is very bright. So these are numbers, basically 10 to the powers. We are not able to grasp them, so I have devised a method to help you understand how bright a quasar is. So go to L5, sit on the first seat, wait till from the universe beginning till today, repeat the step on the second and the third, and until you exhaust the whole seats. Do that twice. So that amount of time, whatever the energy the sun has emitted, the quasar emits in 1 second. So that is basically the energy output of a quasar. So you can basically visualize how much energetic that object is. Now there are actually 4 types of active galaxies. One is the Seyfert galaxy, radio galaxy, a quasar, and a blazar. These are the basic 4 differences. So a Seyfert galaxy, basically these are just a matter of numbers. So a Seyfert galaxy is if the center is emitting as much light as the whole galaxy, we call it a Seyfert galaxy. But if it is emitting more than 100 times or like 1000 times, we say that it's a quasar. Similarly, if there is a galaxy which has these peculiar things, these two lobes which we call radio lobes. These lobes, if you look at it through a visual telescope, optical telescope, you will see only a small dot in the center and maybe it is this. You won't be able to see this because those are only visible in radio light. So that is called the radio galaxy. And this one, if you recognize it, it is Messier 87, the supermassive black hole that we directly imaged. It's a quasar if you look it from the side. Like if this jet is not pointing at you, it's a quasar. If you are looking directly at it, it's a blazar. So if you are standing here, it's a quasar, it's a blazar. So that is just the difference between the position of an observer. Now when I say, if you have read the abstract, you will see there is a line called there are the unicorn, vampire, bat-winged, zebras. Why do you say that? Because they have everything. Stellar astronomers work with optical to UV and all. Galactic astronomers work with infrared and all. But quasars have everything. Each messenger of astronomy is present in a quasar. How? The radio jets, the jets give out radio light. The dust, which is the surrounding dust torus, it gives out infrared and microwave. There is warm gas, which gives out visible light. The hot gas, that gives visible and UV light. The superheated gas, which is around here, it reaches relativistic velocities. It is giving out gamma and X-rays. And the supermassive black hole itself, it is giving out the Hawking radiation, which we do not use in astronomy, and gravitational waves, which can be detected if we have enough things in that. So this is an image of a quasar from the JWST. Now, I showed you an image just before that yeah, all this cool stuff is there. There is a torus and all, and there is a jet and all. But what we see is that just this, a small dot, even in the most powerful telescopes that we have. So, how do we know that all this is present in that dot? So, what is the source of our information? It's basically physics and chemistry, which is just a special case of physics. So yeah, we will be using the physics and chemistry that we learned in our laboratories and some basic maybe common sense and statistics to infer what the quasar is from that dot image. These are the aspects that I plan to cover. These are, I will talk about how do we know these things particularly. There are much more things, but they are beyond the scope of this class, so we will be talking about these particular things. Stars. Now stars, the last stars that we are able to see clearly are in the galaxy itself. So consider that this is everyone knows parallax, right? So this is basically the parallax. This is the sun, this is the earth, and when it's on the opposite side, a star moves around the background. Like when we are here, it looks like that. When we are here, it looks like that. So certain angle is there, and that gives us the distance fairly accurately. So for stars, it's quite easy. It's a simple trigonometric formula. When we move to galaxies, we cannot resolve the stars. So we have to do a particular thing with a special kind of stars called the Cepheid variable. Now Cepheid variable is a star that varies or fluctuates in its luminosity. And the universe has given us a gift that the luminosity of that star and the period is perfectly linear. So if we get the period of that star, we can just count the luminosity. We can just directly by the formula get that. So this is a massive help in the galaxies. So this is the formula. This is the brightness, which we can directly measure from a telescope. Luminosity, which we can get from the period, and d is the distance of that star. So it's a simple formula, quite simple, quite complex as compared to a star, but very simple as compared to a quasar, which we will see next. Now quasars, they are not nearby. They are beyond anything. They are the furthest object that we have ever seen. They are nearly at the times when the universe was just starting. So nearly 13.2 or 13.1 billion light years away. At such distances, cosmology plays. So now we have to apply all that. This is the cosmological formulas for the expansion which we have to take into account, and also, so this becomes quite mathematically robust. Redshift if everyone knows, redshift is a thing which moderates or not moderates, it modifies the light from a source when it travels with respect to an observer. So if your observer is standing right here, if a galaxy is moving here, you see that the wave fronts are squeezed together, so we see that the light has become a little bit bluer because blue has a higher frequency, so it becomes a little bit blue. Whereas from the source which it is retracting from, it will become red. So in the universe, since it's expanding, most of the stuff is going away from us. So most of the things are redshifted. So what redshift is basically if an element emits at lambda naught wavelength, if an atom when excited and falls down emits at lambda naught, when it's moving away, it will redshift, so lambda will increase. So that is a redshift. This is what we use to find the distances of a quasar. This is a particular example. These are the absorption lines. You can see there is no light here. These black lines. All these are shifted towards the right. That is the redshift. So when we look at the light from quasars, we can calculate the redshift, and then we know the redshift, we know the distances. So the distances come out to be massive. Now, for an analogy, again, this is not something that we can understand clearly. You take this paper. If you think that Earth is on this side of the paper, and you scale down the universe so that the Neptune is on this side of the paper. So basically, this paper thin difference defines the distance between Earth and Neptune. Then the furthest quasars will be on the Moon. So this is the scale that we have. This paper thin, if this is the size of the solar system, the quasars will be on the Moon. So that is a particular typical distance of a quasar. Now, how bright are they? So you might have heard that if you are standing on Pluto, the sun looks like you are wearing 30 sunglasses. That is the particular brightness that drops. Same way, if you are looking at a quasar, you will have to wear these many amounts of sunglasses to be able to bring it down to the same level as the sun. That is the typical brightness of a quasar. So that number is 12 into 10 to the power 27. So that many sunglasses you will be needing to bring the brightness of the quasar down to that of the sun. It is that bright. Now we know the distance in brightness. Distance I know the cosmological brightness I have already discussed. Temperature is a bit, I will talk about it later because it's a bit complex. Now the size of an agent. How do we know that the AGN we are talking about is actually a small nucleus of a galaxy and not the entire galaxy that is doing this stuff? So this is the CCD of Hubble Space Telescope. We have CCDs which have a resolution. The resolution of a Hubble Space Telescope is 0.05 arc second. Arc second is basically 1 upon 3600th of a degree, and there are 57.3 degrees in the radian. So by calculation, if an object is a single pixel wide, in the Hubble Space Telescope image which we saw, the 270, it was looking like just a star, a single pixel image. So if there is a single pixel object, the maximum size it can have is 1 parsec. 1 parsec as compared to galaxy is very small, it's nothing. And imagine 100 times that energy of a galaxy coming out from that point. I will give you an analogy again for that. And again, there is a second variability. Now, for variability, imagine there is a bulb right here, and there is a covering. Is it being covered by that? Are you able to see? Okay, so there is a bulb in the center, and there is a lampshade. Let's assume of a distance of a radius r. There is an observer right here. So when the bulb turns on, all of that inner surface of the lampshade or the covering will be illuminized instantaneously at the same time. So light takes certain time to travel here, but that time will be same for everything. Now imagine from this point the light takes t naught time to reach from that point to this point, and from this point to this point it takes t naught. This is t naught. This will take same time, but this is an extra distance. This is r. So the extra time will be r by c. So the point, this point will be reaching you with a delay of r by c. This point will be reaching you at t naught. So there is a particular delay that you will be seeing in the luminosity of a thing. If it is small, imagine it's a bulb. This r is very small, it will be negligible. You see instantaneously it lights up. But if I make it large enough, this thing, if it's huge and r is much more greater than 3E8, what you will see is the brightness of a quasar will go up because this light will reach you, and after a certain time delay, this light will reach you, so it will go up again. So there is a fluctuation. Now imagine this center piece turns off and on, it fluctuates. So if that fluctuation of delta t, let's say fluctuates in delta t, if it is less than this, what will happen is, even before the light reaches this part, it will fluctuate, and so all the fluctuations will be merged together and you will see a continuum. You won't see any fluctuation because all of the fluctuations will be mixed together. But if the fluctuation is much more than this, you will see that the quasar is fluctuating. And that is exactly what we are seeing right here. This is the X-ray from Chandra data. So this is the fluctuation of a quasar. This is X-ray and this is the time. So we can see that it is variation. The variation is happening. So we know that the center object is fluctuating. Now the relation we have is, if delta t is greater than r on c, then only we can see the fluctuation. So if we set the c here, we get a limit. R should be less than delta t into c. So that is the relation that constrains the size of an AGN. Some AGNs have fluctuation within a single day. So if you put a single day time in the seconds of a single day, you will get radius very very small, nearly the size of a solar system, or maybe twice or twice the size of a solar system. So you know that how small the solar system is in our galaxy. Imagine the power of 100 galaxies coming out from that region. Again, for an analogy, the whole that you see right here in this paper. Anyone been to the Niagara Falls? Yeah. So imagine the water coming down from 100 Niagara Falls out of this hole. So imagine this hole is the quasar's AGN. This is the center of a quasar, and imagine the size of 100 Niagara Falls. The water coming down from 100 Niagara Falls, coming out of a single hole in 1 second. This is the energy output of a quasar. And people who cannot imagine Niagara Falls, I have also another with campus. Imagine the rainfall we have on our campus in 1 year. All the rainfall, collect all the rainfall on the campus of 1 year is coming out of this pen cap in 1 second. That is the energy output of a quasar. So we know how powerful these objects are, and probably the most powerful objects in the universe. Now we know the distance, we know the brightness, we know the size of the engine. Now we talk about the composition of the engine. What are they made of? So a typical galaxy has 3 components: stars, gas and dust, and the dark matter. Dark matter contains most of the mass of a galaxy, but again it does not interact with matter, it does not emit light, so we just ignore that. Stars, as we talked, they are absorbed, they give a absorption spectrum. Why? The light in a star is generated inside the core, but there is a shell of gas. So when light comes out of the shell, it gets absorbed. So we get an absorption spectrum from star. Whereas in the case of a dust, it does not emit anything. Whatever the light that star is giving, it will absorb it and emit it in a certain wavelength. So these absorbed energies that you are seeing in that are being emitted here. So the gas and dust give emission spectrum, stars give absorption spectrum. This is the thumb of rule, you can just remember that. So in a particular galaxy, we see a combination of both of them. there are absorption lines, and there are emission lines. So this is basically what a galaxy is made of, and quasars, since we believe they are galaxies with active feeding black holes, we assume also that they are also the same material. This is the spectrum of a quasar. So we can see most of the elements: hydrogen, vita, neon, oxygen, carbon, helium, silicon, magnesium, aluminium, everything is present there. So that is the composition which we get from a single spectrum. But that all of the information that I have talked right now is only from the single pixel image. We know the composition now. All of it is known. Now let's talk about the dynamics. Now look at these. These are just spikes. They are like a spike in the spectrum. They have no dimensions. Whereas these lines are broad. You see the difference? Why is that? Why is the quasar emitting broader lines, whereas the galaxy is emitting a single sharp lines? Because we know that there is a difference, that galaxies are nearby us and the quasar are far away. So the only difference that cosmological redshift will make is this whole spectrum will be redshifted. But why does this broaden? So this has the secret of what is the dynamics of a quasar. That broadening has a special name called the toddler broadening. Now, if there are particles, there will be motion. So there are 4 basic kinds of motion that can lead to broadening. Now imagine there is thermal motion. The electrons are just zapping around here and there. So what will happen is, if an observer is here, and there is a particle here, it's moving here, and one particle is moving here. Chemically speaking, they both should emit at lambda naught, because they are the same element, they have been excited by the same energy, the electrons jump to the same level, they fell to the same level, so they should be emitting both, lambda naught. But this particular particle is moving towards us. So what will happen? It will blue shift. So the energy will be slightly different from that one, and this is red shifted. So we call this lambda blue, lambda red. Yeah. So that will happen in thermal motion because the particles So in thermal motion, what we have is some particles are moving towards the observer. If the observer is sitting right here, these particles are moving towards us, so they will be blue shifted. These are moving away, they will be red shifted. So instead of lambda, some of the light will be lambda plus, lambda minus, slightly above and below lambda. So instead of getting a single peak at lambda, you will get slight values right here and some values here. What will happen is the curve will broaden. The peak will start to get broad. The more number of particles at the higher velocity they have, the broadening will increase. So that is the first kind of motion that can give rise to the broadening. Second is collapse and expansion again. If we consider the observer here, these will be blue shifted, these will be red shifted, these will be blue shifted, and these will be red shifted. So this is the second kind of motion that can give the broadening. That is random motion. There are gas clouds. It is not homogeneous. There are chunks of gas which is just moving around here and there, and again the same concept. And then third one is the rotation. Rotation, if the observer is here, all these will be blue, all these will be red because they are moving around. So now we have to find a method of rejecting all and leave one to give us what exactly is happening. This is the formula for velocity of particle because of the temperature. If we give temperature to a particle, it will move at that velocity. So if we look at the velocities of the particles in the quasar and back calculate the temperature will reach 10 to the power 11 Kelvin. That temperature is enough for ripping out atoms like ripping apart atoms, the electrons will be ripped out from atoms. It will destroy the atomic structure. So we know that this cannot be the case because the temperature needed for that is too high. So we reject that thing. That this broadening is not because of thermal motion. If we consider collapse and expansion, if the whole quasar starts to collapse or expand, we will see that the lifetime will be reduced very much, and we won't be seeing that many number of quasars. Since we see a lot of quasars, we know that that's not the case, because else the quasars will be rare, extremely. And random motion. So when you know that when charged particles undergo acceleration, they emit radiation. So if two gas blobs are moving and they are in random motion, they will zoom past each other, and at this point they will have massive acceleration, which gives rise to huge blasts of energy. We do not see that in quasars, so we know that that is also not the case. So the only thing that remains is rotation. Quasars, that broadening is happening. Most of the broadening is happening because the gas and the air is rotating at extremely high velocity. So the part that are coming towards you is blue shifted and that is red shifted. So you see a broadening. So we know that it is rotation. So far what we have is there is superheated gas that is giving out gamma and X-ray, hot gas, UV and invisible, all these things. So in our physics, only one object is able to do that, which is a supermassive black hole. There is no other concept in physics that is able to explain all that. So see, we do not have direct evidence of a black hole. We do not know if there exists a supermassive black hole. This is the only thing that is a speculation. The biggest one is a speculation. So we can only assume that there is a supermassive black hole, but this is what has the most number of proofs. So we will be going with that. So now we have distance, brightness, temperature, size of agent, position, everything. Now we will calculate the mass of the supermassive black hole. A black hole is basically a singularity, theoretically infinitely dense point with zero volume, which is covered by an event horizon. Event horizon is just a boundary after which the electromagnetic wavelength also cannot pass because the escape velocity increases. It is higher than the speed of light from here on. So nothing can pass, it becomes a black hole. So this is the event horizon. In this particular case, we are calling it a Schwarzschild radius, and that is the formula for a Schwarzschild radius. Now, in a typical quasar with 1 day variability, I talked about the variability. So if you consider a quasar is variable 1 day, the size we get is 3 to 10 to the power 12 kilometers or meters. So if you go by that and calculate with the simple formula, we have G, we have to find M, we have R, we have C. Just plug it in, and this is the mass we get, 2p38, which translates to 0.1 billion solar masses. That is the lower side of a supermassive black hole. There are many black holes that are much lesser than that. So this is how we calculate the size or the mass of a supermassive black hole that is present in here. Now how does that power come? How does it become so luminous? How is the energy being generated? We did not talk about that. So now there is a supermassive black hole in the center, and there is dust and gas moving around it. So imagine there are many blobs of dust and down. So what is happening is they all are in the gravitational well of the black hole. So they move in circles around the black hole. In moving so, since they are moving in different directions, they collide. When they collide, they lose their energy, they heat up, and most of the gas is thrown out back again to come back again later. But some of the gas which lost its energy comes into orbit around the supermassive black hole. This process happens again and again till all of those blobs are now in a perfect disk around the supermassive black hole. Now this disk is a Keplerian disk. All the particles are moving in Keplerian orbits. So this part is moving much faster. This is slow and relatively much slower. So there is a viscous force. The particles are dragging because the inner particles are very fast, outer particles are slow. They drag around each other and there is a friction created, which makes them more compact. Because they lose energy, they become compact, and they keep doing that until the velocities reach nearly the speed of light. And when particles with speed of light have friction, generate enormous amounts of energy. How enormous? The only thing more powerful than that is annihilation. Annihilation is when a matter and antimatter come in contact, they vanish. Everything of the mass is converted into energy. That is 100% conversion of mass into energy. Here, 10% of the mass, so 0.1. The conversion factor is 0.1. So 10% of all of the mass that is moving around is converted into energy. That is massive, because in the sun, helium is converted into carbon and all, hydrogen is converted into helium. That has a fraction of 0.7% as compared to 10%. So in a black hole it's 10%, in the sun it's 0.7%. So you see a massive difference between the conversion of it. So this accretion disk is the one that gives the most of the energy to a quasar. Now why doesn't it keep falling in? It's like it's losing energy, it should keep falling in, right? It doesn't happen like that because there is a thing called radiation pressure. We do not see in everyday life because the medium is not that dense. But here the densities are very high that the light, when it moves out, it collides, 100% it collides with something and it pushes things out. So when it is too heated, too much of radiation is coming out, it will push things out. So there is a balance created now. In stars, we call it a heterostatic balance. Here we call it Eddington limit or Eddington balance. Because there is matter falling inside, because of the spiral, and then there is a light coming out from the black hole which is pushing out the matter. So this is the simple balance is created, and this limit to which you can have the luminosity is called the Eddington limit. And the mass and the distance of the accretion is called again the Eddington radius. Yes, the Eddington radius. So, more supermassive black holes will have a larger amounts of gas will be able to come. Larger amounts of gas will have more of the gravitational pressure. So then the Eddington limit will go up. Because since the external pressure is high, the radiation production will also increase proportionally. So the Eddington limit is related to the mass of the supermassive black hole and hence the Schwarzschild radius.
So it is equal to
Proportional, right? Also, these things you are seeing, these eyes you are seeing this is a quasar, a single object, looked at from different angles, we name it differently, because the properties are different. From here, we say it's a Seyfert 1 galaxy. When you go here and the light is coming from the dust, we call it Seyfert 2. When it's coming out from here, it's a low power quasar. When it's coming from here, it's a high power quasar, and all that kind of differentiation, which I'm not going to go into because it's boring as well as so now we know all this distance, brightness. The temperature I just picked off, but I can talk about because, as I said, this is the accretion disk. Here the temperature is very high, a bit lower, a bit lower, a bit lower, a bit lower. So it's a rings of temperature. The temperature is finally reduced by the Eddington mass and the Eddington limit. It's quite a change. So it's a gradient. So all the integration over this disk will give the temperature of an alien. So that temperature is calculated by the luminosity, like how much luminosity is being generated, how much temperature is needed to generate that luminosity. So it's a integration over the disk. The temperature is not a single thing, it's an integration. Now we have two things here, jets and the magnetic. All everything is clear. Now the jets. Jets. So this is again this is the AGM. This is the center of the supermassive black hole. This yellow you are seeing, the orangish blue is the galaxy, and this is center. This central thing is the AGM, which is powering the quasar. And this outburst is the jet of that quasar. So we do not exactly understand how they work because how bizarre is that? Imagine you fill a sink with water, you plug out the drain and the water starts to swirl. Now all of a sudden the water starts to throw out at the speed of light. It is that bizarre. Because just before this I was looking at the things are moving in circles and all of that. How did suddenly something that is moving in circle at the speed of light, you know the angular momentum. The angular momentum is massive. how do you convert such a massive angular momentum into perpendicular, which needs the most amount of change? So we do not exactly know. That is still a matter of research. We do not know how does that happen. But since we have jets, we can talk about a little bit of the properties.
Perpendicular, what sense?
Perpendicular to the
plane of the galaxy.
Yes. If this is the accretion, it will just pop out perpendicular.
The matter of the jets, is it just radiation or
It's matter. It's plasma. It also, so basically it is matter here, it's charged particles. After it goes a certain distance, it loses its energy and it starts to become a blob. So it's coming out in jet and then starts to form a blob. Here it will generate radiation. That gives the radio wave. This is a jet and that is a lobe. So jet and lobe.
that picture you showed, is that an artistic question or?
This one? This is the real image. This is M87. The supermassive black hole that we imaged, the first image of the supermassive black hole is of that. There is a supermassive black hole sitting right in the center. We saw the image in 2019. And so it was this, and this is the lobe of that.
Just invisible.
Yes, it is. A very peculiar thing also.
The galaxy you showed earlier with the two lobes. Earlier,
Yeah.
very earlier.
Yeah.
This is the actual image of the galaxy. Yeah, this one, the radio galaxy.
Yes, yes. Oh,
Yeah.
that one.
That was
Centaurus.
one of the examples of the jet, right?
Yes, those are jets. So we do not see the jets now, we only see the lobes.
Like the effect of the jet.
Effect of the jet. That jet is dead now. Those are the leftovers. That is a very, very peculiar galaxy, very interesting galaxy. If you look at the spectrum of that galaxy, it will give you an elliptical galaxy spectrum. But that thing,
Does not.
how does that make sense? Because if you look at it, it's reddish, and it does also have a bar.
Yeah, exactly.
So what did happen? Actually, it was a deadly collision between an elliptical galaxy which ate up the spiral galaxy. So what happened is there was a supermassive black hole in the center of both. The spiral galaxy came and collided. The dust made a toss. When they collided, the supermassive black hole turned on. It became active. It threw a jet, and now it's dead. So this is a murder scene. The galaxy was killed here, and so that is, these are like, you can call them blood spots and.
How do you know exactly that the other galaxy was exactly the spiral? Like,
Sorry?
the other galaxy which collided with the elliptical, how do you know that?
The leftover we have here contains elements that only a spiral galaxy can
By spectrum.
To all phases produce jets.
No, not all. If we know the exact mechanism how jets are created, we'll be able to predict which exactly, but since we do not know that, so it's a matter of chance. So that's why there is a distinction. That's why the radio galaxy is a separate galaxy, because these do not produce. That is a special case, it might. Yeah, talking about jets. Now, what is the size of that jet? Any idea? It's huge. So if you take this ring in my hand, and place it on the southernmost point of India, here, at Kanyakumari, and consider this is the size of the solar system. This is the size of the jet. So if this ring is a solar system, the jet will reach Kanyakumari, from Kanyakumari to Kashmir, if this is the solar system. So imagine the huge size of this jet. So this basically nothing. If this jet hits the solar system, it's gone. So I'm not going to go into the details of how jets exactly form because that is not known. But jets are particles, charged particles that move on and then become a blob and they emit radio waves. So this is the radio image of that same thing. So what you see is there is a central engine, AGN, it is throwing out a jet which is flowing like a wave, and this is the temperature plot. You can consider it a temperature plot. So what you see is it's hot gas moving around in the galaxy. So if this is the center, and if you think that this galaxy is this big, so this thing is doing a very particular thing, I will say. So when two galaxies collide or a galaxy is new, it is actively forming stars because it has got new gas and new dust. So all of the things so if a galaxy forms, there is starburst. Stars are being created here and there. So when stars are made, the environment around them is very hostile. They are being bombarded with ultraviolet light. The conditions are not applicable, life cannot be formed. So when I say the quasars created life, is that because when they switch on, they throw out a plume of hot gas which heats up the galaxy. Now when the galaxy is heated, the star formation drops. Because for the stars to form, the cloud must collapse to form a star. And a heated cloud cannot collapse. So when the quasar switches on, it kills the star formation and gives way to life. Now this is the Andromeda quasar, which will be forming in when the Andromeda galaxy and the Milky Way will collide. There is a supermassive black hole in both of the galaxies. When they collide, the black holes will have turbulent flow or turbulent throwing of material here and there, and they will get active. They will start feeding, and the Andromeda will become a quasar for a short time. That quasar will kill the star formation, and again the life will be created if the chances are perfect. So yes, the quasars were the slayers of the galaxy in the earlier epoch, and they helped us create life and made a way of creating life. So that's how I conclude the talk.